Great. Well, hello everybody. Welcome. Pleasure to be here. I'm not in person, but pleasure to be in Liverpool nonetheless. So, why we should build a moon base? So I don't know whether I normally ask at this point whether anyone recognises this moon base. I can kind of see the lecture theatre. If anyone in the if anyone in the lecture theatre recognises this moon base, I might see you put your hands up. I don't see any hands going up though. You have to be of a certain age to recognise this moon base. This is Moon Base Alpha from Space 1999, which was a TV series in the 70s. And you can watch these, they're all on YouTube. Anyway, it's a fantastic series about a moon base. But so we were supposed to have a moon base like this in 1999, and here we are 23 years later, and we still don't have a moon base. But I think there are good reasons why we should have a moon base. So that's what I'm going to talk about. Now, obviously, I come from a scientific background, and there are a lot of scientific reasons for wanting to go back to the moon, with or without a moon base. But I think a moon base would greatly help some of the science. So that's what the talk's mostly going to be about. But of course, there are other reasons. Anything really big and expensive that happens in space is going to require multiple reasons, and science is only one of these reasons. So we can conceive of economic reasons for wanting to establish infrastructures on the moon, and these would be short-term economic benefits for like the companies that involved and the people employed, but also possibly long-term economic benefits in the use of lunar resources, which I might touch on at the end if I have time. Geopolitical benefits. Obviously, the Apollo program was a geopolitical program, but it was kind of a negative geopolitics because it was all done in the context of Cold War competition. But I would like to think that there's a positive geopolitical reason for returning to the moon, provided it's done as an international activity. And this would be as a focus of international cooperation. And I also think expanding to the moon and then throughout the solar system more generally, but starting with the moon, is likely to expand human horizons quite a lot, and that this could have cultural, many perhaps unforeseen cultural benefits as well. So mostly I'm going to talk about the scientific case for returning to the moon, but if I have time, I might touch on some of these others. Now that's interesting. When I've got the laser pointer working, I can't advance the slides by pressing the arrow, but I can do it if I do that. So that's interesting. Right. So I just wanted to say a little bit about the history of lunar exploration before we start into the future, and a little bit about the legacy of the Apollo program, which came to an end 50 years ago. So December 1972. Was the last Apollo mission to the moon, and I think it's important to point out just how, although we haven't been back to the moon since with people, we're still mining the legacy. The scientific legacy of Apollo has been enormous, and we're still benefiting from that today. But of course, this also sets the scene for the kind of things we'd want to do on the moon in the future. So this photograph shows Jim Irwin from Apollo 15, and here he is preparing the lunar roving vehicle. So Apollo 15 was the first Apollo mission with a moon buggy. There's a tall mountain in the background. This is Mount Hadley. It's about 4,000 meters high. And I just for the scientists and for, I don't know whether there are any geologists in the audience, but I draw your attention to this rover's being kitted out essentially to enable geological field work. These are plastic bags at the back of the rover. These are the sample bags in which rock and soil samples were located. And there's a stash of tools. You can't see it very well, but a stash of tools, tongs and rakes and things at the back of this vehicle to help collect these moon rocks. So the Apollo missions returned a relatively huge quantity, 382 kilograms of rocks and soils, which have led to much of what we think we know about the moon has been built on a study of those samples. But as will become apparent, there's a lot of the moon that hasn't been explored, a lot of the moon that we don't have samples from, which we would need to address particular scientific questions. And so this is the basis of wanting to go back to the moon, as will become apparent. So very brief slide on the history, the legacy of the Apollo samples. I mean, some of this seems quite prosaic, but really important in planetary science. And the pictures are kind of generic. The top is just a generic Apollo. You see it's Apollo 16 sample, based sample number begins with 6. But it's really just there as a pretty picture to show you that large bits of the moon were returned by the Apollo missions. Picture at the lower right is a bit closer to home. It shows some these black grains of basaltic soil samples collected at the Apollo 12 site that we've been studying at Birkbeck for a while now. In fact, there's a picture of 3 of us in the receiving facility in Houston, taking possession of these little Apollo 12 soil grains. So there's yours truly in the middle. This is Katie Joy, who's now Professor of Planetary Science at Manchester University, and Josh Snape, who's now also recently moved to Manchester as well. Anyway, so this is just our personal involvement in studying some of the Apollo samples. Anyway, what have we got out of these samples? So the first thing seems really boring, but really important from planetary science perspective is that once you've got rock samples in the laboratory, you can date them using some radiometric dating scheme. And if you've got these, if you collect samples from surfaces, say lava flows, on which you can count the number of craters, this is a way of deriving an absolute calibration of the cratering rate. And that is important because it means you can date once you've calibrated the cratering rate, you can date surfaces from which you haven't collected samples, provided you can count the craters, which is relatively easy. But you can only do that if you've calibrated the cratering rate to start with. Sorry, that's my telephone. Hello. Sorry, I do apologise, the perils of giving these talks at home. Anyway, once you've got a cratering rate calibrated, then you can estimate the ages from places where you haven't collected samples from, including other planets. So all of our estimated ages of surfaces of Mars and Mercury, even Venus, these go back indirectly, at least, to the calibration of the lunar cratering rate, because we haven't got any dated samples from any of those other planets. So this seems a bit boring, but it is really important legacy of Apollo. Second bullet point is that we've got, obviously, by collecting moon rocks, it's taught us a lot about the geology of the moon itself, and I'll say more about that, but later. What we also learned from studying, especially soil samples, like these Apollo 12 samples in the picture, is that we learned that meteoritic material is implanted into the lunar soils, but so is solar wind, and so are the products of galactic cosmic rays. So there's a potential record on the moon of meteoritic contribution into the moon, but therefore the moon's been orbiting the Earth all this time. So meteoritic and solar wind and galactic influences that have involved the moon, but they've also involved the Earth as well. So that's a potentially valuable historical record for understanding the evolution of the habitability of the Earth over time. And last but not least, once we've got rock samples collected from known locations on the moon, and therefore we can know what these samples are made out of, we can compare that with what the orbiting spectrometers think these bits of the moon have been made out of, and therefore we can use this to calibrate orbital remote sensing instruments. So that's a brief summary of some of the things. I mean, I could give a whole talk on this, but a brief summary of the scientific legacy of the Apollo samples. It's also important not to forget that Apollo deployed a wide range of geophysical equipment on the moon, which has helped us constrain the interior structure of the moon, of which the picture at top right here is a paper published in Science about 10 years ago now, gives our current best view for the interior of the moon based on Apollo geophysics measurements. So it's got a small core relative to its size, but certainly has a core. The core is liquid on the outside like the Earth. Anyway, we've put all this together based on studies of the Apollo geophysics measurements. Picture at The top right here shows the Apollo 14 seismometer. This is it here, connected to its communications and power supply box. Picture at lower left. This shows the only planet in the solar system, apart from the Earth, where active geophysics, seismic profiling, has been deployed. I mean, this is an important geophysical technique used on the Earth for probing the near-surface crustal structures. But it's only been done on the moon, apart from the Earth. This little black box with the laser pointer, just above the laser pointer, this is one of 8 explosive charges that were deployed by the Apollo 17 astronauts. And these explosives were detonated after the astronauts left the moon to provide signals for a seismic array that was deployed somewhere out here. You can just see the Apollo 17 lunar module in the distance there. Picture in the middle shows Apollo 15 astronaut David Scott deploying a chain of thermocouples, which he's about to lower into the lunar, into a 2-meter deep borehole that he's just dug to measure the heat flow coming out of the lunar interior. And picture at bottom right, you'll recognize, is one of the Apollo laser reflectors, which are still used today, where laser beams are bounced off these reflective mirrors, essentially. And then the time delay from the Earth and back gives us a very accurate measurement of the Earth-Moon distance, and therefore has enabled us over the last 50 years to quantify the rate at which the moon is receding from the Earth. Anyway, the point is we wouldn't have all this information without Apollo, so this has left a very rich legacy. But it's also very important to realize that much of the moon is still totally unexplored. So this picture, you see the near side of the moon on the left and the far side on the right. I've drawn on this map the now 10 locations from which lunar samples have been returned to the Earth. So in the whole history of the space age, we've still only got 10 locations on the lunar surface with rock samples returned to the Earth. And these are the 6 Apollo landings, the 3 Russian robotic sample return missions from the early 70s, Lunars 16, 20, and 24. And then just 2 years ago, the Chang'e 5 samples collected by China's first sample return, robotic, of course, sample return mission from the moon. So if you look at this and you were to draw a line around all of these, I mean, Chang'e 5's sort of mid-latitude, but most of them are roughly equatorial, low latitudes anyway, all on the near side. Nothing really in the southern hemisphere of the near side, nothing out on the western limb of the near side, nothing at either pole, and no samples at all from the far side. So this still means there's a lot of the moon still to be explored from a geological point of view. Now, I've restricted this diagram to the sample return locations. Of course, there has been, if we plotted all robotic landings as well, there'd be quite a lot of points, but there'd still only be one point on the far side, and that was China's Chang'e 4 spacecraft that landed in 2019, I think, about there where the laser pointer is. So still only one successful soft landing on the far side and no samples returned from the far side. So the point here is there's a great deal of the moon that's still waiting to be explored. So the science that would be supported by a return to the moon, some of these, strictly speaking, although I'm here advocating for a moon base, not all of these would actually require a moon base, at least initially, but many of them would benefit from establishing a significant human presence on the moon. At least that's going to be my argument. Anyway, if I just go through this list of bullet points, this is written up in this short article I wrote for Astronomy and Geophysics a few years ago, should anyone be interested. Obviously, by exploring the moon more, we'll learn more about the moon itself and its geological evolution. And that is important because the moon is a representative of a small rocky planet whose own internal geological activity shut down a long time ago. Now, that makes the moon sound boring if it's geologically dead, but it's actually very important because it means that it preserves a record of the earliest evolution, geological evolution of a rocky planet, and then it's become frozen in time. Whereas more active planets like the Earth and Venus and even Mars have had such long active geological periods that their geological histories that a lot of their earliest history has been eroded or obscured or buried, whereas the moon preserves this. So I'm thinking of things like the earliest crust that planets form after their initial magma oceans start to crystallize. This is preserved on the moon as far as we can tell, but not on any other terrestrial planet. So this is a geological reason for, well, except possibly Mercury, but the moon is easier to access. So this is the top bullet point. Second bullet point, I'm going to talk about a little bit in a bit more detail, if I may, because it's become something that's started to interest me a lot over the recent years. The moon as an archive of solar system history. This shows Jack Schmitt, Apollo 17 astronaut. So this picture was taken almost exactly 50 years ago. But the key thing is to note that the lunar regolith that Schmitt is walking over here is totally exposed to the space environment because the moon has no atmosphere, and because for most of its history it's had no magnetic field. Charged particles coming in from space, like the solar wind or cosmic rays from the galaxy, impinge just unimpeded on this dusty surface. And so there is a potential record here of the evolution of the sun, using the solar wind strength as a proxy, and the solar system's location in the galaxy, using the galactic cosmic ray flux as a proxy. Over billions of years of history. It just requires us to access regoliths of the right appropriate age and then extract the solar wind from it and the cosmogenic products of galactic cosmic ray bombardment. Next bullet point I've got is the moon is a potentially useful platform for certain types of astronomical observations, especially radio astronomy. Come to that in a bit. Ditto life sciences investigations. I'll say a bit more about that later as well. And finally, if we want to explore the rest of the solar system, there's a lot of stuff we have to learn, a lot of capability that's going to have to be developed. And it strikes me the moon is the logical place to start learning how to operate in what are really pretty hostile conditions, low gravity worlds with zero or very thin atmospheres, with a challenging radiation environment and a lot of surface dust. So the moon is a place where we can learn to mitigate those problems if we wish to later explore Mars or other places in the solar system. So I'm now going to build on this as argument for returning to the moon, and in particular building up an infrastructure, which would include a lunar base and things that a lunar base might facilitate. So here's this graphic that I got from a NASA website, and it shows some explorers on the moon. I just want you to look at this and notice there's quite a lot of infrastructure in this picture. There are some astronauts. I don't know what these astronauts are doing. They could be scientists, they could be tourists, they could be prospectors. But anyway, whatever they're doing on the moon, their activities are supported here by a lot of infrastructure. There's a local transportation infrastructure in this moon buggy. There's an interplanetary transport infrastructure in this rocket to get people on and off the moon. There's a habitat infrastructure, and all that would need with its solar, with its power supplies and everything. Anyway, my argument is going to be that by building up an infrastructure like this, science will benefit. And actually, I think a lot of science will get done that wouldn't get done otherwise. And my key analogy here is with the Antarctic research stations. So, picture at top right, this is the Amundsen Scott base at the South Pole, and it facilitates, like the other Antarctic research stations, facilitates a lot of scientific activity on the Antarctic continent that wouldn't happen without this permanent scientific infrastructure in place. So just as some examples going around this slide, every Antarctic summer, field scientists go out into Antarctica on snowmobiles. I mean, they get deployed by light aircraft and then set up temporary camps and then operate out of the temporary camps with snowmobiles to look for meteorites that are found on the Antarctic surface. So these Antarctic meteorite collections activities really wouldn't be practical if there wasn't a permanent research base from which the scientists could operate out of. Picture at the in the middle here. This shows a graphic of the Lake Vostok. So Lake Vostok is a body of liquid water. It's 3 kilometers underneath the ice, and it's below a Russian station, the Vostok station. And it was discovered by scientists at the Russian Vostok station conducting a seismic survey. And then they discovered the subsurface lake, and then they've drilled into it, and that hasn't been an entirely happy story. But the point is, only by having a permanent research station at the surface here, namely the Russian Vostok station, was this subsurface lake discovered, and only because a permanent scientific infrastructure existed was it possible to drill down and access this lake. And that's enabled the access to this lake that wouldn't be possible otherwise. And of course, subglacial lakes like this are taken as analogues in an astrobiology context for similar subsurface lakes that may exist on Mars, and also subsurface bodies of water in the icy moons of the outer solar system. Anyway, the exploration of these Antarctic subglacial lakes is also facilitated because of a permanent scientific infrastructure. Picture at bottom right, you may recognize this is the IceCube neutrino, I think it's called IceCube, neutrino detector, which is operated at the South Pole to detect neutrinos, because the neutrinos interact with the ice, and the ice has been drilled through with photomultiplier tubes to detect the Cherenkov flashes as neutrinos interact with the surface. So this is an astronomy facility at the neutrino astronomy facility at the South Pole. And picture top right here shows the Antarctic dry valleys, which are probably the closest analogues we've got to Mars on the Earth, and are widely used by astrobiologists as a Mars analog location. Anyway, the point is, all of these activities and more, we could observational astronomy, atmospheric science, geology, obviously, zoology, all of these sciences are facilitated in Antarctica because of a permanent scientific research infrastructure that's been built up over the decades. And my argument is that something similar would happen on the Moon and later on Mars, but the Moon is the place to start. So I'll try and go through some of these relatively quickly, because I think I've already probably made the essential point. Expanding the first bullet point in the question, what has Apollo ever done for us? Then the first bullet point was calibrate the cratering rate, and that's, yeah, it's prosaic, but it's important planetary science. The one thing the Moon has is a lot of craters, and this is the far side, Highlands. This is a crater, about 190-kilometer crater called Daedalus in the far side of the Moon. The point is, if we could date all of these craters, or many, many more craters than we've currently dated, which we can do, it just requires taking more samples from more craters of a wider range of ages. We would have a better calibration of the cratering rate of the Moon, with all of that, the advantages that has for planetary science, including the dating of other planets for which we haven't yet got samples from. But there are a few key things I do wish to highlight. So if you look at the graph, it says log impact rate relative to present versus time. But this shows the first half of solar system history. So from 2.5 gigayears ago to the origin of the Moon, somewhere out here. And we don't actually know what the impact cratering rate was in the first billion years of, well, perhaps a bit less than that, first 800 million years or so of the Moon's history, partly because none of the Apollo samples were derived from terrains that were that old. So we could get a better calibration on that by sampling older surfaces than Apollo was able to do. And that's important because we haven't got any dated samples from the first 800 million years or so of the moon's history. There are several possibilities for what the cratering rate might have been doing. And in particular, there's uncertainty as to whether it was following a relatively smooth monotonic decline, which is the dashed line, or whether it did something like this, a precipitous fall in the impact rate immediately following the formation of the moon, then a period of relative quietness between about 4.4 and 4.0 and 4.4 billion years ago, followed by a spike, often called the heavy bombardment, followed by a decline to the present value. Anyway, the point is, this is a logarithmic scale. So the uncertainty in these between the dashed line and the solid line actually is orders of magnitude difference in the impact flux. And this is an important time period because this is the time period sometime prior to 3.8 billion years ago that life became established on the Earth. And from an astrobiology point of view, we'd very much like to know just what was the impact regime on the early Earth under which life originated. And we don't have that answer on the Earth because there are no Earth rocks that old left for us to study. But the moon does preserve a record of the impact regime at the time that life was becoming established on the Earth. So from an astrobiology perspective, that's quite an interesting thing to want to know. Second thing that the moon has been collecting over solar system history probably are volatile compounds like water, but also probably other volatiles, carbon dioxide and organic materials, coming in to the Earth-Moon system from the outer solar system, or at least from the asteroid belt. And this picture shows the south pole of the moon. This is taken by the Japanese Kaguya spacecraft, probably 10 years ago now. This geographical south pole of the moon is about there, just where the laser pointer is sitting. On the rim of a 20-kilometer diameter crater. This is appropriately named after Ernest Shackleton. Spacecrafts flying over the south pole of the moon towards the Earth, and because the south pole of the moon is the right way up from our northern hemisphere perspective, the Earth looks upside down. So here you can see the continent of Australia, I hope. Anyway, the point is there is a lot of shadow in this picture, and that is because at the lunar poles the sun is always on the horizon. And that means the interiors of craters at the lunar poles are always very cold because they never see the sun. 40 Kelvin would be sort of typical. There are places where 25 Kelvin has been measured with the radiometer on the Lunar Reconnaissance Orbiter spacecraft. So at temperatures of like 40 Kelvin, water ice is stable under a vacuum. And there's now growing evidence that these permanently shadowed regions at the lunar poles contain water ice. This water has probably come in from the outer solar system, and it probably has entrained with it other volatiles and organic materials. So there's a potential record here by accessing these polar ices. There's a potential record of the extent to which volatiles and organics have been brought into the inner solar system and therefore to the Earth. Throughout large slices of the age of the solar system anyway, which would be very interesting to know about, again, largely from an astrobiology perspective. Of course, if there is water ice in these permanently shadowed craters, then that will also be very useful from a future resource perspective. So there's a tension here that at some point is going to have to be reconciled. Science is interested in these ices as a record of volatiles delivered by comets and asteroids to the Earth-Moon system. Future people who want to operate on the moon, including future scientists who might want to operate on the moon, would benefit greatly from having a local source of water, because that's a source of water, of course, but it's also a source of hydrogen and oxygen. And if you don't have to carry that stuff from the Earth, that would be, and because you've got a local resource, that would be highly beneficial. So, but there will then be a tension we might talk about later if we have time, of how to preserve the ice for the scientific study, but also allow people who want to explore the moon and the rest of the solar system and want a local source of water. There's going to be anyway, how that's managed will become important, I think, in the coming years and decades. So the next thing I want to talk about is I would at this point pause and ask whether anyone's got any questions, but maybe it's just easier doing it this way if I just carry on. I'll just take a sip of water. I'll switch a light on. Right, so this reason for wanting to go back to the moon picks up the point I made earlier about the Lunar Regolith being a record of early history of the solar system, including the sun and the galaxy. I've here added something else, though, that I think is also possibly great interest. So I've listed these 3 bullet points under the general head of treasures in the regolith, scientific treasures which I think are or potentially could be waiting to be dug up in the lunar soil. I'll come to the top bullet point last, if you don't mind, since I've already mentioned the next 2. So this is Buzz Aldrin's boot. So this shows the Lunar Regolith from Apollo 11, and so we get a good sense for its structure. Anyway, however long this regolith has been exposed on the lunar surface, solar wind particles have been implanted into it, and we know how to get them out. We found that if we heat Apollo regoliths to about 700 degrees Celsius, the solar wind implanted gases, hydrogen, helium, argon, carbon dioxide, nitrogen. Well, carbon dioxide is a bit interesting, actually, because probably that isn't just from the solar wind. These gases can be extracted. And so there's a potential record here of the varying strength of the solar wind through time. Galactic influences, e.g. supernovae. Every time the solar system has been, I mean, the solar system is currently in a pretty boring part of the interstellar medium. But there will have been times when the sun's journey around the galaxy has taken it to more exciting parts of the interstellar medium, perhaps dangerously exciting parts. And if the solar system were to wander close to an exploding star, for example, there would be a sudden increase in the cosmic ray flux. Cosmic rays impacting the lunar soils. What happens then, the cosmic rays are mostly relativistic protons, but then they strike atomic nuclei in the soil and convert whatever the target nucleus was to something else. So these are called cosmogenic nuclides. And by determining the rate at which cosmogenic nuclides have been produced in lunar soils, there's a potential record here of the varying flux of galactic cosmic rays throughout the time the soil has been exposed. I'll come back to that. But before I do, the bullet point at the top, terrestrial meteorites. Now, we have on the Earth a few hundred meteorites from the moon, and we also have a few hundred meteorites from Mars. It's very likely that there are Earth meteorites. Since we know that planets exchange meteorites, it's very likely that there are Earth meteorites on the moon. They'd have got to the moon by some giant meteorite impact hitting the early Earth, bits of the Earth's crust being knocked out into space, and these eventually intercepting the moon, and then there would be a terrestrial meteorite on the moon. So here's Aldrin's boot, and here's a rock. Now, I've no doubt at all this rock, you see it casting the shadow, this rock will just be a moon rock, I'm sure. But there will be places on the moon where rocks could well be ancient parts of the Earth. And if we could identify those, they could be really valuable. Obviously, we don't need samples of today's Earth because we've got plenty of those. But if you think about the Earth's geological record, I mean, the oldest Earth rocks we've got are about 3.8 billion years old, perhaps slightly older if what are they called, the Acastonices in Canada, There aren't very many of those. We've hardly got a geological record of the Earth for the first billion years of Earth history. And that's because the Earth is such a dynamically active planet, and it's eroded them and buried them and metamorphosed them. But that means we don't have samples of the Earth's crust from this key time period in Earth's history when life became established on our planet. If we could find bits of the Earth dating back, say, 4 billion years or 4.3 billion years, and we could use those to constrain what the Earth's crustal environment was like at that early time, this would help us better understand what the Earth was like at the time life arose on our planet. Well, we're most unlikely to find such ancient Earth rocks on the Earth, so strangely, the moon may be the place to find them, and it would involve finding ancient Earth meteorites. Now, they will be really difficult to find, which is why we're unlikely to stumble across them unless we're already doing a lot of stuff on the surface of the moon. And this would be an argument for the kind of large-scale activities that would be enabled or facilitated by a permanent scientific infrastructure, such as you would get with a moon base. The chances of you landing with some robotic spacecraft at some random location on the moon's surface and stumbling across an Earth meteorite is just infinitesimally small. It would require a really large-scale search. Anyway, coming back to the second two bullet points, the solar wind and the galactic influences. Sorry, it's the wrong way. So picture on the left shows obviously a large solar prominence. And the idea here is every time we have solar flares, then we have enhancements in the solar wind, which means that a more active sun sends more solar wind through the solar system, which means more solar wind is implanted into lunar soils. Picture on the right, so you may recognize this galaxy. This is Messier 51, and I just have it here as an example of a spiral galaxy. But of course, our solar system, if this were our galaxy, our solar system would be somewhere here in some inter-arm region, perhaps somewhere there. It takes the solar system to about 200 million years to orbit the galaxy. So although the solar system is currently in a rather uninteresting place, there will have been times, multiple times in the history of the solar system, and therefore the history of the Earth, when the solar system has passed through spiral arms and may have been close to exploding stars, and when it's had a significant chance of passing through much denser than average interstellar dust clouds. All of these, or both of these, may have had effects on the past habitability of the Earth. And so it would be useful if we had a record, and the record primarily would be a record of changing galactic cosmic ray flux. So if we had a really, and that is preserved in lunar soils and rocks, as I mentioned, usually in the uppermost few meters, which is a depth to which the cosmic rays penetrate. So if one would, and so the moons, as the moon's been going around the galaxy, probably 20 times since the solar system formed, it's been exposed to this changing galactic environment, exposed to a changing galactic cosmic ray flux. And if we could extract the cosmic ray products from dated rocks, we could eventually, if we studied enough of them, of a wide range of ages, start to see whether we can correlate the cosmic ray flux with the spiral pattern of the galaxy. So this is kind of like, both of these arguments are kind of like arguments for doing astronomy from the moon, but instead of arguments for putting telescopes on the moon, which I'll come to in a bit, it's kind of using the moon's geology, the rocks of the moon itself as a kind of giant telescope to infer past historical activities of the sun and the past locations of the sun in the galaxy. So how to extract this information? I think this is again where geology, so I don't know the backgrounds of people in the audience, whether people are, I won't ask for a show of hands, but in principle, I don't know, there might be astronomers and or geologists and or biologists in the audience, or I should have checked. Okay, sorry, so mostly geologists. Oh, good. So this is where geology can really come to the rescue and help astronomy. So if I just go back, What we know from Apollo is that solar wind particles and galactic cosmic ray particles are implanted, or the solar wind particles and the products, the nucleogenic products of galactic cosmic rays, are preserved in the lunar soils. But if you take and we can extract that we have extracted those signatures from the Apollo samples. But if you consider all Apollo did was sample the current surface of necessity, because that's the way Apollo worked. I mean, the maximum depth was 3 meters for Apollo 17 drill. So this regolith here of Apollo 11 is about 3.8 billion years old. So yeah, it preserves a record of solar wind and galactic cosmic rays for the last 3.8 billion years. But the problem is there's no time resolution. All you've got is a integrated summation of what the sun was doing and the galaxy was doing over 3.8 billion years. And that isn't really what we want. What we want is a time resolved picture of what the sun and the galaxy were doing at specific times in the past. So this is where geology comes to the rescue, and it comes to the rescue through the stratigraphy of lunar lava flows. So I'll start with a picture on the right. You imagine a lava flow is placed on the moon. Micrometeorites impact the surface and develop a regolith. Regolith then acts like a giant sponge and collects solar wind particles and stuff coming in from the galaxy. But then, if this regolith is then covered up by a later lava flow, it becomes trapped at that point, and from now on I'll call it a paleoregolith. And the point is, the paleoregolith is now an ancient regolith, but it's isolated from the space environment. So the process starts again at the top. New regolith developed, new stuff gets implanted into the new younger regolith. But anything in this paleoregolith, if we were to drill through this lava flow 2 into the paleoregolith and then back down into lava flow 1, and we were to extract from the paleoregolith cosmic rays and solar wind particles, and because we've also got samples of the under and overlying lava flows that we can date, everything that we find in this trapped regolith comes from a well-dated time horizon. So because we dated the under and overlying lava flows. So so then we'd know what the sun was doing and what the galaxy was doing in this particular time window. And if we will find enough such locations on the moon, and there will be zillions and zillions of such locations on the moon, eventually we could construct, in principle, a time-resolved record of the evolution of the solar wind and the galactic cosmic rays. So since this is a largely geological audience, here's a picture just to illustrate this on the left. These show there's 2 parts of the surfaces of the moon. This is Mare Imbrium, it's on the near side. It's both a lava, everything here is a lava flow, except these craters, of course. But neither of these lava flows have been sampled, but we can estimate the ages because we can count the craters on them, and thanks to Apollo we can calibrate this cratering rate. So we know that the background lava flow here has an age of 3.3 billion years, and this overlying lava flow, which you can see, is going to be younger because it's just stratigraphically on top. Anyway, you count its craters and it's 3.0 gigayears. So if one was to set up a drilling rig where the laser pointer is here, it's about 50 meters thick here. Drill through about 50 meters, you'll come to a paleoregolith that's been developed on this older lava flow before it was buried. So by drilling through here into a paleoregolith underneath that's sitting on top of this 300 million year old lava flow, that is where, if you wanted to know what the galactic cosmic rays were doing 3 billion years ago, but within a 300 million year old interval between 3.0 and 3.3 gigayears, that is the information you would hope to find. But of course, it'll be obvious to you that in order to build a complete record of the history of the sun and the galaxy, you're going to need to do this in many, many different places with with a wide range of different ages. And that's going to require, well, there are several possibilities. There are places where ancient lavas and trapped regoliths outcrop at the lunar surface. So one could visit these outcrops. Picture on top left shows the wall of Hadley Rill that was visited by Apollo 15 again, which is a lava channel. Photographed. The Apollo 15 astronauts didn't clamber down into this rill because they'd never have got out again, but they did photograph the wall, and there are these bedded lava flows, which will have bedded regoliths in between them probably. There are these very interesting collapse pits on the moon, only three that are of order 100-meter size. Very strange, because these are not impact craters, they're collapse pits. So this implies a void underneath, like a lava tube that's largely uncollapsed, but has collapsed in one place. Anyway, the point is there are these collapse pits. Where they occur, they reveal the lava flow stratigraphy of the surface lavas that make up the bit of the moon wherever these things are, and you can see the clear layers in this lava, layers of lava flow piled on top of each other in this part of the moon. So you could imagine the word has abseiling, yes. You could imagine abseiling down this cliff, probably with a robot abseiler, sampling lava flow regolith, lava flow regolith, lava flow regolith, lava flow regolith, right, and build up a picture of, and then extract the solar wind and the cosmic rays from these trapped regoliths and build up a historical picture. So this would require accessing the outcrops. That in itself implies quite a bit of infrastructure. You need mobility to get to these outcrops, and if you're going to start abseiling down cliffs, you need all that equipment and everything. There will be many places on the moon where these lava flow layers exist, but they don't outcrop. And so one could access those, but you'd have to drill for them, like I've said in the previous example. So this would be an argument for drilling. And we do a lot of drilling on the Earth to access subsurface geological things that we're interested in. The point here is it requires quite a lot of kit, right? It requires the drilling rig, the ability to troubleshoot the drilling rig when it goes wrong. Then you'll be faced with like tens or hundreds of meters of core sample. Someone has to decide, presumably locally, which are the important bits of that core, which can be studied on site, which are so important they're going to have to be shipped to the Earth. All of that is going to require quite a lot of stuff on the moon to do properly. And so it's the kind of large scale activity that, again, I think would be facilitated by a large permanent infrastructure like a moon base. Now, at this point, I would normally pause and ask for questions on the geology, but I think in the interest of time, I'll just quickly push ahead with the two other scientific reasons for wanting to return to the moon. Astronomy from the moon. So in a sense, my whole paleo-regolith argument has been like asking for what can lunar geology tell us about astronomical questions. But in addition to that, the moon is a plausible location for certain types of astronomical observations, and especially radio astronomy. I don't know, on my screen, I've got a little picture and it shows you, and you may have a little picture that shows me, but is it partly obscuring this diagram?
No, fine.
Oh, it's fine. Okay, right. Thanks. So the diagram at the top shows a picture of the opacity of the Earth's atmosphere, and therefore the way as a function of wavelength, and therefore the wavelengths that astronomers on the Earth can access. So where it says 100% opaque, this is astronomy you cannot do from the surface of the Earth. So X-rays, gamma rays, most of the ultraviolet, you have to be in space to see those wavelengths of light because they don't penetrate the Earth's atmosphere. Then we've got the visible window. Then we've got the near infrared, some of which gets almost through to the surface, like at 10 microns, and other bits don't. Then we've got the far infrared, which is totally opaque. This is why the James Webb Space Telescope has been launched and built, because it can access these wavelengths that you have to be in space to do. Then you've got the radio wavelength, the radio window. So locally in Cheshire, obviously we've got Jodrell Bank, and so the radio telescopes on the Earth's surface can access radio waves from space, reach the Earth's surface, except that only up to a wavelength of about 20 meters, because beyond the wavelength of about 20 meters, the Earth's ionosphere becomes opaque. So once again, you have to, if you want to do long wavelength radio astronomy, longer than about 20 meters, yeah, you have to be in space. And it would be ideal to be in space in a radio quiet place. Now, the best place in space that is totally radio quiet is the far side of the moon, because the far side of the moon never sees the Earth. So it is totally shielded from artificial radio noise. And during the lunar night, of course, on the far side, it's also shielded from the sun. So for 2 weeks, then you've got the most radio quiet place in the solar system, and no atmosphere and no ionosphere. So long wavelength radio waves would reach the lunar surface unimpeded. And there is a lot of science to do at these long wavelengths, actually. I mean, I know this is a geological talk, but from an astronomy point of view, mapping the earliest galaxies, or the structures that formed the first galaxies, will require mapping neutral hydrogen clouds. Neutral hydrogen has a spectral line at 21 rest wavelength of 21 centimeters. It sits about here, and radio astronomers study the 21 centimeter hydrogen line to map hydrogen clouds in the galaxy and the local universe. But at the time the earliest galaxies were forming, because of the expansion of the universe, the 21 centimeter line is redshifted out to beyond 21 meters. So if you want to study hydrogen from the earliest galaxies, you have to be at a wavelength that doesn't get through the Earth's ionosphere. So this would be a key scientific reason for setting up a radio telescope, at least on the far side of the moon. Here's an artist's drawing. Just to say, a kind of start has been made. It's not a radio telescope yet, but this picture shows the Chinese spacecraft Chang'e 4, which, like I said earlier, was so far the only spacecraft to land on the far side of the moon. So this is what the far side of the moon looks like. Looks much like the near side of the moon. But there's a large aerial here that would go up and up and up off the picture. And this is the first radio science experiment that's been done on the moon to determine just how radio quiet it really is. So I'm not aware of the results from this experiment yet, but it's kind of you can see how it will build to us gradually assessing whether the far side is such a great place for radio astronomy as we expect it to be. And then final scientific point to talk about is something about life sciences. So I've got a lot of information on how microgravity affects life because of many experiments and space stations over the years. Picture on the left shows Tim Peake on the space station engaged in a muscle atrophy experiment. What we don't have, because the Apollo missions were not long enough, is any serious data on how low but non-zero gravity affects living things, including how it affects humans. Obviously, the gravity on the moon is 1/6 of what it is on the Earth. So does this mean that we have the same muscle loss and the same immune system degradation that we have in microgravity, only it just takes 6 times longer? Or do the things not happen at all because some gravity is enough? Maybe there's a gravity threshold. Maybe 1/6 of a gravity is enough to stop you losing bone and muscle, or not to affect your immune system. So we don't know, but we do have to learn before we start sending people to Mars on multi-year missions. Just what are the long-term effects of low but non-zero gravity on humans, but also on our microbiota that we need to survive, and other living things that we might need to take with us to survive, like plants and agriculture, these things that may be not so important for the moon, but could become very important if you wanted to set up a Mars colony sometime in the future, we would need to know what are the effects of low but non-zero gravity on living things. And the moon is probably by far the best place to start figuring this out. I'm aware that I'm just about hit my hour, 5 minutes to go, but just to also leave you a thought about another astrobiology related life science reason. This picture shows the ascent stage of the Apollo 11 lunar module. So when this picture was taken, Armstrong and Aldrin were in here, and it's about to dock with the Apollo 11 command and service module. You can tell it's on its way up because it's obviously doesn't have its legs. The legs have been left behind. Nice crescent Earth background. Anyway, once the Apollo astronauts had returned from the lunar module ascent stage into the command and service module for return to Earth, these Apollo ascent stage years were crashed into the moon. And this was done deliberately to provide data for the geophysics experiments, to provide data for the seismometers that had been left behind. Anyway, the thing is, these Apollo lunar modules had two men living in them for 3 days, more or less. And when they were inside the lunar modules, they obviously took off their space helmets and everything. These vehicles would have been full of microorganisms, and then they were crashed into the moon. So the question is, what happened to these microorganisms? I mean, one would expect many to survive for 50 years on the moon. On the other hand, lots of nooks and crannies in a crashed space vehicle. You can think of circuit boards and possible nooks and crannies where microorganisms, even if they're not active, many microorganisms can hunker down into a cryptobiotic state, a sort of a spore-forming state. It would be very interesting to visit some of these crash sites to see whether any microorganisms that were certainly present when the vehicles crashed have survived, and if they haven't survived, what kind of organic molecules are left as a residue, because this would help us inform our questions relating to planetary protection, important for Mars, of course. Questions related to panspermia as a hypothesis as to whether life can survive long enough to travel between planets naturally. We could kind of get some insights into this by exploring places on the moon where we know we have introduced living things, albeit microorganisms, and see how they've done after 50 years. It seems an important and it seems a relatively simple experiment to do, but then you think about what is required, right? The transportation you need to get to these sites, the handling of the samples, the return of them to the Earth for analysis. All of this is going to require quite a lot of stuff, the kind of stuff that I think would be facilitated by a research station, an Antarctic style research station on the moon. So I probably don't have time. If anyone's got any questions, I can come back to this slide. This is the moon may have resources, geological materials, which are of value, if not in value for importing to the Earth, certainly a value for exploring the moon, and maybe a value for exploring elsewhere in the solar system, given that it requires much less energy to lift stuff off the moon into space than it does the Earth into space. So it's probably going to be a very long time before lunar resource extraction is on anything of this scale. But it is worth thinking about. But it could become a future. The moon could become important as a source of natural resources, at least for the further exploration, the continued exploration of space, even if not for the importing into the Earth's economy. Only 2 more slides left. So I said at the very beginning, I was going to, I didn't promise to have time to talk about social, cultural and political benefits and a focus for international cooperation. I think a return to the moon could help in all of these respects. But I just have time to just mention what I think is perhaps the most important of them all. And it's perspective. This picture shows the first time human beings really saw the Earth as a planet in its natural habitat of the solar system, really. This is the Apollo 8 Earthrise image. This is the North Pole of the Earth here. South Pole. This is the western part of Africa, Sahara Desert up here, South Africa just down there. Anyway, the point is, you get to you don't have to get very far from the Earth to see the Earth as a planet, and it starts to look pretty small. And so this perspective is really, I think, could be one of the main non-scientific but cultural benefits of exploring the universe, starting with the moon, is the more people who get to see this perspective and realize that, you know, we're all on this Earth together. It's the only habitable planet we've got. It's not really very big. Maintaining its continued habitability is really important. Fighting territorial wars of aggression over little bits of this land surface doesn't really make a lot of rational sense. This perspective is could be important, but I think I've said enough. And so I'll just show you anyway. This is my last slide. So this is another quite ambitious moon base, modernized a bit from Moon Base Alpha and Space 1999. This is a recent ESA graphic. Of course, any first setup of a lunar research station would be a lot smaller and less developed than this. But over time, we might imagine quite a sophisticated moon base being built, and maybe more than one eventually, and maybe similar establishments on Mars and perhaps elsewhere. But I think the moon is the place to start, and I think it would yield all of these advantages, scientific and otherwise, that I've tried to outline. So thank you, Liam. I'll leave it there.